So now we'll start our presentation for this evening. Remember to keep your questions in the chat. Keep yourself muted, please, and we'll answer questions after our presentation. So tonight we have very special presenters. The first one will be Charlie Hammond, who is a senior engineering geologist with Cornforth Consultants, which also has a division of landslide technology, and he's been with them since 1987. He's investigated landslide and rockfall hazards and their risks, seismic hazards, soil and rock material sources, groundwater and dewatering, soil and rock tunneling, and other complex geologic hazard issues. Mr. Hammond is a professional engineering geologist in Oregon and Washington and a hydrogeologist in Washington. He has a BA degree in geology from Whitman College and an MS degree in geology from the New Mexico Institute of Mining and Technology. Our second speaker tonight after Charlie will be Brent Black, who's also a senior engineering geologist for Cornforth, where he's worked for over 28 years. His areas of expertise include rockfall and rock slope evaluation and mitigation, landslide stabilization and site investigation, geologic hazards assessments, and construction quality assurance. Brett serves on the board of the Engineering Geology Committee and the Rockfall Management Subcommittee for the Transportation Research Board of the National Academy of Science, and is the chair for the subcommittee on landslides for that organization. Mr. Black has a BS degree from West Virginia University and an MS degree from Kent State University. And I've worked with these folks for close to 20 years, and I can tell you they're top notch for unsurpassed knowledge of the Clackamas River Basin. Now let's welcome Charlie and Brent as they present about the geologic hazards of Oregon. All over to you two. Thank you.
Thank you, David, for asking me and Brent to join us this evening and share some of our information and background in the Clackamas River. As you've gave us our introductions, we're senior engineering geologists with the firm Cornforth Consultants and its division Landslide Technology. The company was founded in '83 by Derek Cornforth. He had a knack for understanding behavior of subsurface materials, geology, soil, and rock. And he wanted to do business in helping out people with foundation issues and dealing with slope stability. And it's not just landslides and rockfalls, it's embankments, dams, canals, tunnels, bridges, a lot of infrastructure, utility corridors, these kind of things, highways, roads that have to deal with slope stability issues. So we're a local company, 25, 28 strong here in the Portland area, but we work all across the Western United States, sometimes in the Eastern United States. We've had a couple of clients that are overseas. So I've been lucky, I guess, to first step foot professionally in the Clackamas River drainage basin back in the late 80s, maybe 88 or so. And but I had grown up in the Portland area, so I've done a little bit of rafting and hiking up in the mountains as a youth, Boy Scout, and later type of things. But now I'm a professional. I've been working in this basin for a few decades. So some of our clients are the Department of Transportation, which deals with the roads. We've done work with Federal Highway, who manages the forest roads in the forest, or helps the forest out in some of their studies, but also Portland General Electric, who's got their facilities up along the Clackamas River. So we've been up working with them to help them with their foundation issues and their maintenance of their projects. So let me just jump into a basic overview. We're going to talk just really quickly about the geology. Thanks to Clark last presentation a couple of weeks ago. He gave a really nice overview, but I can just touch base on that real quick. I'm also just going to kind of step through some of the geologic hazards. But as I do that, when I think of dealing with geologic hazards, I kind of have a list, a cheat sheet that I kind of go to that talks about what hazards we want to investigate if we need to. But I'm going to use some of the hazard maps that are presented that are available online through the state, U.S. Geological Survey, and other groups So I'm going to kind of use those to help us look at what kind of hazards we have in the Clackamas River. And then I'll spend a little bit of time looking at some high profile hazards with the help of Brent and some of the things that are in the press that we've heard about and we may have been involved with in the past. So the first thing is just a quick look at the basin itself. So this is just a map. On the left is the state, the Willamette River Basin. Let's see if I can get my laser pointer thing here. So there's the Willamette Basin and then the Clackamas River in black, and on the right, basically the whole outline of the Clackamas River. The lower Clackamas River portion, Clear Creek, the Tickle Creek area. As you go upstream, there's the Eagle Creek. As the Eagle Creek goes up into the higher, rugged, more mountains in the upper drainages. But then this middle part, this is basically a roughly just upstream from Estacada is what I think of as the upper Clackamas River Basin. But I can also think of it as a middle Clackamas River, and that's this stretch through that's got the Roaring River and the Fish Creek, because that's the steep canyons of the Columbia River basalts as you're going up into the drainage basin. And then the uppermost, the Oak Grove, Upper Clackamas River, and the Polowash Basin, Polowash River. So just keep the shape of that drainage basin in mind, because we'll reuse it as I walk through some of these slides. So Clark had given us an introduction on the geology. He got into a little more detail than I'm planning on to right here, but I just wanted to show this is the geologic map of Oregon. This is a map that's available online through Dogami. You can look at this map. It's a state map, so it's not real detailed in the real precision that you can get on individual quads or something like that. But this gives you a great introduction to the geologic materials of the state. And you can click on each one of these shapes, and it'll give you information of where what the colors represent, where the data came from. So it's a database that I go to quite a bit when I want to learn about the geology in a cursory kind of high level point before I go out to a site, or to find more detailed information embedded within it. But the basic three main components of material that make up the basin are shown: the high Cascades in the red, the Western Cascades in kind of the blue, and then the Willamette Valley in the yellowish part. And this is a very generalized separation of them. It's a lot more complex. Good old geology is a lot more complex. There's a lot of interlayering. The high Cascades is the young volcanics of the Cascade Peaks, and the older high Cascade materials that are 2-3 million year old rocks that underlie the high mountains. But underneath that is the Western Cascades. That's the older decomposed 20-30 million year old volcanic rocks that are the foundation of the Cascades. And those, between, I guess, the upper part of the Western Cascades and the lower part of the high Cascades the high Cascades are sitting on top of a formation called the Rhododendron Formation, which interfingers with the Columbia River basalt. The Columbia River basalt interfingers or is overlain on top of some of the older Western Cascades materials. So that blue area is a complicated package of the rocks that are real familiar to many people in Oregon as the Columbia River basalts. But the things that aren't as familiar are the old part of the Cascades. And that's an integral part to some of the hazards that we'll get into here later today. The Willamette Valley is got a whole package of materials, including the Columbia River basalts, but there's also the younger sediments, the terrace gravels that the Clackamas River deposited in the lower part of the basin. And then there's the boring lavas, which are equivalent to the older part of the high Cascade materials as far as age. It's basically a complex package of material. It's hard to be generalized to it, and I don't want to go into more detail. Clark has it that we saw a couple of weeks ago. So just a short list of geologic hazards. So I'm not sure the order that I put these in. I just thought that they would work here. So one of them is seismic ground motion. So the movement during an earthquake. There's also volcanic hazards in the area. Flooding is another geologic hazard. I kind of think of it as an environmental hazard because it's more than just the geology. It has to do with the climate, precipitation, and snow, but the geology has something to do with the shape of the basin and the way that the ground holds groundwater. But fire is another thing that is not necessarily a geologic hazard itself, but it does impact some of the geologic hazards that we have. And Brent will talk a little bit about some of those things that we're seeing. Another geologic hazard that's not a real issue significantly. Well, there is some radon issues. I think of a natural concentration of materials. Clark had mentioned that there's a cinnabar mine up in the basin. So that's, a natural concentration of an environmental contaminant material, but radon is getting to be more known in the Oregon area as an issue. So that's one of the hazards that's out there. There's also, I think of as erodible soil as a hazard. Some soils are more susceptible to erosion, the silts and sand kind of material. And then there's also expansive soil. That's another type of hazard, but there's not a lot of that material up in the Clackamas River. And then the big one that we deal a lot with is slope stability. So landslides, rockfalls. We could talk about seismic stability, but that's a little more of a specialized kind of understanding of the impact that seismic has to do with ground motion, has to do with slope stability. So one of the sources that I use for looking for information is the Oregon, the Dagami database statewide geohazards viewer. So you can get online and look at the geologic hazards. So what I've done is I've just traced the outline of the basin, and we're just going to walk through some of these hazards that are in the basin and beyond it. The first slide was just kind of a basic terrain model that shows you the ruggedness of the slopes and the rivers, the valleys, and this is another database that some of us are real familiar with. The gray that just came up on the screen is the available ground that has been surveyed using the LiDAR, the light detection and ranging method of measuring the ground surface or what's on the ground. It's an airborne laser, and it's a new technology that started coming out in early 2000, and it's extremely useful for what we deal with geologic hazards. And the gray is basically the coverage. You can see that the lower Clackamas River drainage is completely covered with that gray, but then upstream from Estacada up about Promontory Park, a little bit further, then there's just a corridor that follows along the river, the Clackamas River, and then up the Oak Grove Fork up to Timothy. And I'm suspicious that it has to do with PGE's work up there, and they've been instrumental in collecting that information. There's also another small patch up here. I'm curious about that one. I don't know why it was. I haven't looked into the data, but I could probably find out. But I did take a look at it, and we'll show a couple of images here later on tonight. So this first one is the hazard map. Again, this is part of the statewide hazards viewer. This is the Cascadia earthquake expected shaking. So they have the colors. The deeper red is violent, then the red being severe, then orange being very strong. So the lower part of the Clackamas River Basin is in this very strong motion, which is about just showing it. I just typed in some numbers here to show what does that mean, when you feel a very strong motion. And so it's about, 20% to 35% of the gravity, the force of gravity. So this orange part they've projected, and this comes from U.S. Geological Survey studies and all the data about the Cascadia earthquake. The upper drainage basin is in the strong motion. There's red within the basin in small areas, and I'm pretty sure that those are related to existing mapped landslides. So the mapped landslides are expected to move and shake and amplify the motion a little bit, so they have a little bit more of a ground motion. So that's where it lies in the Cascadia earthquake shaking map. The next one is the basic generalized earthquake hazard map. So here we're looking at the influence of the active faults, which are highlighted in the purple. So at the or violet there at the lowest part of the drainage basin, there's a number of faults due to some good geologic mapping that has been done. There is not a lot of information on active faults in the middle. I think that's a figment of the conditions and the mapping. There just hasn't been a lot of good mapping. There's likely to be some faults in there that could be active, especially with the upper basin. There are some faults that are assumed to be active. The expected ground shaking is very similar to the Cascadia subduction zone between strong and very strong and strong motion. This map is also related to earthquake hazards. This is a map that has to do with susceptibility for liquefaction. So liquefaction, you need high groundwater and sand or silt. That size of a grain size material with a high groundwater where ground shaking can cause it to liquefy and cause ground to move. What's in the Clackamas River is basically, again, I think the landslides fit within this, not necessarily that I would agree with the landslides that liquefy. But the main thing, I think, is just the lower Clackamas River. Some of those terrace gravels may fit that classification. I think that would be a stretch to make those kind of materials liquefy, but there may be local zones within those sediments that are predominantly sand that could liquefy. This I just wanted to show you because, you know, that we don't have a lot of earthquakes in Oregon. They just are not very frequent. But this map is a map that shows each of these little blue arrows is a very detailed GPS movement. So a geographic movement of the ground. Okay, there's an arrow down here. I think this length of this arrow is 25 millimeters per year of movement. So down in Northern California, there's a lot of movement, and then up in in Washington, there's quite a bit of movement. So what are some of these vectors? Maybe they're 15 millimeters per year of movement. So this is, tectonic plate movement. Some of the things that are on this map are the plate boundaries, earthquakes, epicenters, the volcanoes that are associated with the tectonic activity. I also drew in the little Clackamas River drainage there in red. So there's not as much earthquake movement or earthquakes occurring in the Oregon because the movement is just a little less than it is to the north and to the south. But the movement, the tectonic activity is occurring. That's the main point about this, is that we do expect earthquakes to continue. They're just not quite as frequent. Back to the statewide geologic hazards map. This is the volcanic hazards. In red, the proximal areas around Mount Hood and Mount Jefferson to the south of the basin, showing the areas that could be immediately impacted by volcanic hazards. And there's also the orange of the Sandy River and coming down off of Jefferson towards Salem, in the debris flows that come down those drainages. So, a couple hundred years ago, that's when the crater rock on the top of Mount Hood was a result of the eruption that happened a couple hundred years ago. This picture in the lower left is not Mount Hood. It's not that eruption, but I think someone just found a picture that this might be what it looked like when that eruption occurred. There were pyroclastic deposits, there was some ashfall, but it wasn't a big voluminous ash eruption. And that's one thing that Mount Hood, Mount Jefferson, compared to St. Helens, St. Helens has a very large ash hazard, where in the geologic history, the ash deposits that occur from Mount Hood are just not as large. And so I think when they do these maps, one of the issues about ashfall is which way the wind is blowing. So if the wind is blowing the normal direction, which is towards, from the west, any ashfall from Mount Hood is not going to get into the Clackamas drainage. But we do know that a little bit got in there from St. Helens, but that's not a big hazard. So basically, the Clackamas River Basin is somewhat isolated from the volcanic hazards that are right nearby. This map is the flood hazards, and the blue and purple are the FEMA. Well, the blue is if you're familiar with the flood maps, it's a 100-year flood. And you can see, if you zoom in on it, you can see where it's been identified as a 100-year flood area. So it's just the lower part of the Clackamas River. But again, these are online databases you can easily get to and see the information. This map is the radon. Okay, so radon comes from the Columbia River, the ancient river deposits, the Troutdale sediments, the sands and gravels that are in that. They're also in the flood deposits, the Missoula flood deposits. Any kind of material that's got the granitic rocks that come from eastern part of Washington, Idaho, that have come down in Canada from the Columbia River. That's the material that's brought in the radon. That's the source of the radon. And there is this, some of these maps are kind of odd. One of the things that you look if you're familiar with geologic maps, why is this area so square? That's not a geologic boundary. That's probably some kind of a property line or some limit to the study that was done when that map was put together. So this brown is the high radon potential, where the lighter brown is a moderate radon potential. But I'm sure that this is a broader area that is not just limited to those lines. But like the eastern part of Portland, there's a lot of the old ancient river deposits, the Troutdale Formation, and then on top of those are the flood deposits from the Missoula floods. So there's not a lot of it in the lower Clackamas River, and I think some of these actually correlate with some Columbia River basalt layers. So I'm a little questioning some of these maps here, but definitely the radon maps are not as detailed as they can be. I think they're going to improve with time as that hazard becomes more aware. Okay, so now we're looking at landslide hazards. This is the map that shows the very high reddish are identified as existing hazards. That's a good thing to do. The landslide likelihood. Okay, this is landslide susceptibility map. Okay, so an existing landslide is highly susceptible for reactivation. So that's the deep red. The high hazard is in the orange, and then the moderate hazard is in the yellow. Basically, the maps are based on the density of known landslides and the slopes, and the statistics between the density and the slopes. They do also think about the landslide prone materials. So one of the things that I haven't got into more detail is the geologic formations that are susceptible to landslides. And Clark talked about this when he was speaking a couple of weeks ago, but the Western Cascades, the ancient Cascade deposits are very susceptible to landsliding. And that's this deep red material. There's a lot of landslides up in that area. And then down in the lower part of the Clackamas River, they're following the exposures that are on the along the rivers that are exposures of the Troutdale Formation, where the bottom of the Troutdale Formation has got a very fine grain facies deposit that's called, I think it's been called the Sandy River Mudstone, that's sitting on top of some rhododendron kind of formation. So that Sandy River Mudstone is susceptible to landslide, but there's another fine layer of sediment within the Troutdale Formation that's typically on top of a nice conglomerate layer, but there's a fine grain facies within the Troutdale that is also very susceptible to landslide. When we zoom into some of these areas, we'll see that. So that's the lower part of this area is all the Troutdale Formation landslides. And this is just the inventory map. So on the same database, you can click on any one of these shapes and get information on where the map is and dig into more information about why that landslide is there. And I think we'll start to look at it a little bit more closely as we get into some of the trying to think, I thought I had a slide here that says, okay, we'll start looking at some of the specific high profile hazards. Maybe I'm jumping ahead of time, but anyway, so here's the lower drainage basin. You can see there's a number of landslide features. These are all landslide deposits in the ground. They basically are following this is our Troutdale exposures along the river. The red dots are fan deposits, like debris flow deposits. This map shows the area that's the LIDAR, and the LIDAR we'll get into a little bit of detail here as we go. Let's see, I'm down in the lower basin. Then this next slide, I'm looking in the middle part or the upper part. So just to the top of the screen up here is the North Fork Reservoir Promontory Park, and then the narrow gorge of the Clackamas River coming up. And then here's the river coming upstream. Here's the confluence with the Oak Grove Fork. So from here, the Oak Grove Fork goes up towards Timothy, and then the Clackamas River keeps on coming to the south. And then at this point, there's a confluence to the Colowash, goes down, and then the Clackamas River comes off here to the east and heads up further. And I think then this is just the most upper part. And again, one of the things that it shows is the LIDAR outside of the basin is complete to the west, but the upper part of the Clackamas River Basin has very limited LIDAR coverage, while there are some significant areas of landslides mapped up there. Okay, so this is just kind of a summary here of, okay, this is the slide that I was thinking about where I'm going to start talking about some of these high profile slides. But the main hazards in the main geologic units, the alluvium, colluvium, landslide deposits, those are the young sedimentary materials that are in the geologic column, the materials that are in the Clackamas River drainage. The hazards that are in those materials are erosion and ground movement. The Clackamas River terrace deposits, those are down in the lower river. I think I missed going through each one of these things when I was talking about the geologic maps, but basically those are the spring water formation up in the upper part of the terraces, but then down in the flatter areas near the rivers, there's also sedimentary terrace deposits which are susceptible to some erosion and shallow landslides. Then there's the high cascade deposits where they have rockfall, debris flows. But the ancient river deposits, those are the spring water, the spring water, the Troutdale and the Sandy River Mudstone, which is kind of what I think of as a fine grain facies at the base of the Troutdale. Those are very susceptible to landslides. And then the Western Cascades and the Columbia River basalt. The Western Cascades have this rhododendron, sardine, beds of Bull Creek. The beds of the Bull Creek materials are the deeper, older material. And then the sardine, rhododendron, I kind of think about them as the same material, are decomposed volcanic tuffs, tough breccias, like old cascade type mud flow deposits and things that are quite widespread and highly decomposed and very susceptible to sliding on the weak rock conditions because they've decomposed to clay. And then the Columbia River basalts that have their own rockfall issues. So here we're going to zoom in on a few slides that we've had some experience with. Okay, so the first one is right down at the near the beginning of the river, the mouth of the river. This is a geologic map. Here's another plug for the National Geologic Map Database, NGMDB. This is put out by the U.S. Geological Survey. This is a compilation, online compilation of all the geologic maps that are published in the United States. And this is a great source of information that I use a lot. You can find where you want to go and click on it. Here I've clicked on this one map that's visible on the screen, and up on the left side pops up that map. And if it's online available, you can click on it, download it. You can also zoom in it. Some of these are not available. They're out of print or whatever. They're just never been scanned. You can still access them online and get the information from them. So here in the circle is the slide. I think of it, I called it Forsyth Road. It occurred back in the big storms of 95, 96, I think the winter of 95, 96. This here's a LiDAR map. I don't know what the year this was, but this was more recently in the 2000s. So Forsyth, okay, here's the edge of the river, the bank of the river. So this is the part of the river. This is the Clackamas River Road. Many of you have probably driven on that. At the top of the slope is the Forsyth Road. I'm going to go back real quick. So the Clackamas River sediments in yellow, the QTT, this is the Troutdale Formation. So basically we're in the Troutdale Formation. The LiDAR, just real quick, what we're looking at here is the ground surface. The data, the digital data can be processed to remove what's on the surface, the trees, buildings. You can look at the data, remove that upper surface and see what is bare ground. The other things that are in there, the resolution of the data can be visible. You can see the faceted surfaces where there's not a lot of information. Maybe the trees are really dense. But basically what you see is the Forsyth Road. There's a ditch on the uphill side, and on the outside, it basically follows the top of a slope. And there's a bench and then some steeper slopes that go down to the river. So this was a geologic map, and I don't spend a lot of time on it. I just want to go to a cross section, but basically this was a map from the old timers. This is a Spencer Gross map from photogrammetry, aerial photographs, doing the survey work from photogrammetry to make these topo maps. But this is where it worked well for us back then. There's a bench along the highway, and then a pretty steep slope that goes down all the way to the Clackamas River. So this slide was big in the press because of, well, I think it was just, there was excitement on some state geologists that saw that this slide was there, and he said something in the press about the slide. It could block the Clackamas River or something. So there's a lot of news. There was a president flying around in a helicopter when we were out there doing the reconnaissance. And but when we got out there, we were like, okay, this is just a slide up on the top of the bluff, and there's some debris flows that are going down, and you know, putting material on the road. But it wasn't that significant of a landslide. I mean, yes, it was affecting Forsyth Road, and it was causing a little bit of siltation in the river, but it was mainly affecting a house here and the road. And in cross section, basically, on the lower right, it doesn't go all the way to the Clackamas River, but the base of the slope is the Sandy River mudstone. There's a cliff of the Troutdale gravel. And then above the gravel is a sand deposit. And then there's some upper layered interbedded clay and sand, the fine grained facies of this Troutdale formation. So the slide was only 30, 40 feet thick. And it went down and it slid within one of these clay layers, and it was towing out on the top of the cliff and dropping over the edge. And I mean, this geometry of this slide is very common up and down this area of the drainage. So as you go back and look at the geologic maps, you can see these slides following the drainages. They're very common in this sequence. So here's a geologic map that was done by Maiden in the early 90s for Dogami. Here's the community of Carver. There's, how many people have driven the Highway 224 through the narrow part with the cliffs on the north side. There's the Madrone Park. Clark was talking about that with the red is the boring lava, but the green is the Troutdale Formation, and these were mapped landslides. Even Maiden mapped the landslides, but when you look at the LiDAR, they're more common. Okay, so here's the LiDAR with Dogami's database. This is another database. This is just a slope shade from Google Earth on the terrain, and this kind of shading helps these landslides stand out so much more. So here's the Madrona Park, is these cliffs for climbing is right in here, but this whole area, I mean, there's just landslides all over the place. All these drainages, these lower drainages, there's slides all over the place. So are they moving? Some maybe, some of them are so old and ancient, maybe they're not moving, or maybe they only move during the most extreme weather conditions. But anyway, that's kind of an introduction to those landslides that are very common up and down those drainages in the lower basin. So the next area that I'm going to look at, so Estacada is just to the top here, and then we're just a little bit upstream towards the Portland General Electric's Faraday powerhouse facility is right in this area. This is the Faraday forebay. There's a canal that goes up. There's a diversion dam, but then the water is retained in North Fork Reservoir. So I've got two circles here. I'm going to talk about this slide, and then Brent's going to jump in and start talking about this, and then something further up drainage where the basin, the valley gets very narrow and steep in the Columbia River basalt. But here on this landslide, this was a slide that I started working on in, I think it was 88, 89. And it's just on the upstream side of Faraday Lake. This again is another geologic map of the area that was done by Schlicker in '79. This is very common, an early precursor of the geologic hazard maps that are very good maps from this period. But we're in an area called the Sardine Formation, decomposed volcanic tuffs, flows, but there's not a lot of rock. It's very hard soil, dense soil like rock because it's so decomposed. The upper areas are overlain by the boring lava, and I think there's more boring lava on this side of the river also. But let's zoom in at this area in LiDAR. The Clackamas River flowing from right to left along my laser pointer. Here's the canal that's bringing water into Faraday Lake. There's a landslide between the two of the river and the canal, and then there's another landslide on the upstream side. And what we can see in the LiDAR are the mitigation efforts that were done, the berms and buttresses that were built on the landslide. So I'll show a cross section of the lower one first. I didn't get around to making some colors here, but the canal, when it was constructed back 100 plus years ago, there was material placed on the downstream side that basically was a narrow area. The canal was placed on a hillside here. The founded materials on the ground surface were the terrace gravels. This is the older spring water type kind of formation that's sitting on top of the decomposed tuff breccia. And this is the material that was susceptible to sliding. So the load from the embankment is what was causing the ground to move, especially when this area was filled later on. So the canal was built in 1907, but in the 60s and 50s, or the 50s, that more material was placed out here, and that's the thing is what caused the ground to move. So in this little inset diagram is what was put out there is to, there was a rock fill buttress that basically loaded the toe, holding the toe of the landslide in place. And then there was material removed from the upper part of the slide to remove some of the load. So just the improvement of the stability, there's about a 20–25% improvement of the factor of safety in that landslide. So that was all that was necessary to keep that hillside there. On the upstream side, this is a little more simpler diagram, but the canal, the slide was towing into the canal. Again, it's moving in within the tuff, the old decomposed Western Cascade deposits. The clay layer is the same thing. It's just completely clay. And then there's an andesite rock that's part of the old Western Cascades also. But the same kind of thing, we excavated out the material in the canal and replaced it with rock fill, then put a buttress, and then removed the upper part of the slide and made the slide 23% better than it was. So it's a factor of safety of 1.23 in this design. So these are common slides in this area they have a rotational slope, but at least in these things, but the slides may have been joined at one time before the canal was built. We just didn't, the canal, the whole slide wasn't moving when, as the mitigation was done. It was just one was stopped and then the other one was stopped a few years later. And then we start to go further upstream. So this one I'm going to hand off to Brent and let him take over. So Brent, you want to share your screen? You can take it over for me.
Yeah, let me make sure I can figure this out here. Well, thanks, Charlie. And so I'm going to talk about a very specific type of geologic hazard, and that is rockfall and rock slides. So Charlie's done a great job of showing you how well the state of Oregon's been served by USGS and specifically Dogami with all these great maps showing all these geologic hazards. But I also want to talk a little bit and give a little props to ODOT. Back in 1984, ODOT started the first rockfall hazard rating system, and it was the first in the nation. And it has since become copied by a lot of states nationwide, and Federal Highways has actually adopted this program. And what the rockfall hazard rating system is what ODOT did is they went and they inventoried every single rock slope adjacent to their highways and then systematically rated them for geologic hazards and rockfall hazards compared to each other. So it's an incredible undertaking, and it's just a very valuable resource to compare relative hazards of rockfall compared to other sites throughout the state. And federal highways actually they adopted this system. And when a manual was produced by federal highways to teach people how to do the rating system, this picture in here was put in the manual. And this picture here is a slope from Oregon 224 along the Clackamas River. And what this system does is it rates all slopes and gives them a preliminary A, B, and C rating. And then the highest rated slopes or the highest hazards get an A rating. So A is not good in this category or in this rating system. A is bad. And this slope here that happens to be along the Clackamas River up in our drainage basin is one of the top 10 worst sites for rockfall hazards in the state. And actually the 224 corridor, I think, has the most or the second most A-rated or the highest hazard rated slopes in the state. And so I'm going to be talking a little bit about rockfall up in this area, but just know that this area has a very high potential for rockfall to begin with. And then we're going to talk about some recent events that's added to that, of course. I started out my career not helping ODOT out along their roads, but helping Greg Bush and PGE out with rockfall issues along Faraday Road, which is, like Charlie mentioned, it's the area along the Faraday Dam and the Forebay and the Faraday Reservoir. And just sporadically, they would have, you know, some bigger rocks come down. Sometimes they'd stay in the ditch, and sometimes they wouldn't. And then other big rock outcrop exposures, you'd have some pretty significant rockfall come down and block the road. And a couple of these threatened some towers that supported transmission lines. So it was a problem. So Charlie and I spent a lot of time helping PGA out with that over the years. And then in 2007, there was a pretty significant slide, be it a rock slide that occurred along Faraday Road. And this area is termed as the Biscuit Rock Slide. And I think Clark mentioned the Biscuit Rock, but it got its unique name from these columnar joining. I believe that that's the boring formation, the boring lava formation. And these columns look like stacked biscuits. I've been maybe falsely accused for naming that, but because they look like stacked biscuits to me, or maybe I was just hungry that morning when I went out and looked at it. But it was a pretty sizable event that, as you can see, blocked the road down here. And then as we climbed up on the slope, that slide undermined, as you could see, some very large boulders up here. These things, you know, were giant ball bearings that some of them had been displaced, some of them were in place, but they were perched up on the hill right above the road, which was a major concern because obviously the road, the Faraday, is down below, but downslope of the road is a fish ladder. So that's a major facility there that that PG had concern with. So mitigation was needed. So it started with kind of excavating or hogging all this material out to get us some room to work down here. And eventually we came up with this concept of putting this freestanding gabion basket down here to protect the road and protect the fish ladders you could see downslope of the road. Very critical structure through here. This freestanding barrier is 12 feet tall, about 9 feet wide. you needed something substantial to be able to handle these type of impacts. We knew were probably coming, and it was so wide that actually we had to cannibalize half the road to build it, but we needed something that wouldn't deflect and that would be able to protect this fish ladder. And over the years, it did its job. Some smaller stuff came down. It did that, no problem. You can see the slope was hydroseeded to kind of stop erosion, and all was working well. But we have a saying in the landslide game is gravity always wins. And eventually, back in 2017, during some heavy rains, a couple of those big boys came down and whacked our buttress down here. The buttress worked, it did what it was supposed to do, but that just gives you an example of kind of on this lower end down along the river, the rockfall hazards that are pretty prevalent through this whole area. So now what we're looking at here is an oblique aerial view, kind of looking to the northwest. Along the Clackamas River and down here, and you can see 224. And obviously this is a picture that was taken post September for the Riverside fire, the recent fire that happened there. Most of you probably attending this talk know more about this fire than I do, but it started near Ripplebrook, I believe, and then high winds kind of pushed this fire west about 17, 18 miles along the Clackamas River drainage. And you can just see the extent of the burn in here. I think 140,000 acres were burned. But kind of more importantly, you know, look at this rugged terrain, how steep it is, and just how extensive this terrain is in here. Here's a close-up view along the river. You can see, you know, just the rock slopes, the natural and the cut slopes that are in there. In this area, I believe, especially west of here, was subsequently burned back in 2014. As part of the 36 pit fire, I believe it was called. So after that fire back in 2014, a lot of scaling and a lot of rockfall mitigation was done in the area to deal with the rockfall, the subsequent rockfall that you see after a fire. And now, you know, unfortunately, you know, we just, you know, 6 years later had another horrific fire out there. Here's a view kind of at the road level, looking back to the northwest at 224. And just, you know, think of the potential, just the hazards that are associated with these events. You know, not only do you have the trees burning, extensive tree burnings, and we'll talk about that in a little bit, but all this vegetation, all the moss, things in there that kind of help keep loose rock in place was all burned off. And then that intense heat also kind of inflates rock. And again, this is an area that was a very high hazard rockfall corridor to begin with. And now after repeated burns, it's just only getting worse. And besides, you know, what's going on on the slopes, you know, there's a lot of things that you got to assess before you can come and open a highway. I mean, you all that have driven that know that there's this extensive guardrail along the road to help deflect cars from, you know, if there's a wreck or someone falls asleep, they don't want them going into the river. Well, now imagine all those guardrails have burned. They've been either the wood posts have actually burned and just completely gone, or they've just sustained such intense heat that will those guardrails structurally do what they are designed to do? Can they deflect a car? Or have they been somehow weakened by the heat? And these are things that need to be assessed. A lot of culverts that cross the road to carry the water from the inboard ditch to the outside, you know, historically, they've always been metal culverts. Well, those rust. So here lately, to help mitigate erosion and corrosion, plastic ABS culverts have been installed. Well, it's plastic. Intense heat make those things kind of just shrivel up and pinch off. So now all the culverts need to be assessed. If you look down here to the right, here is a pretty sizable retaining wall. This is a steel bend wall, been there for years and years and years. You know, this retaining wall holds back the roadway prism for 224. So now this area has burned. So structurally, is that bend wall, is the integrity of that been compromised? Is it going to perform as designed? So, you know, there's a lot of things that need to be assessed and dealt with besides the hazard trees and the rockfall I'll show you in a bit before you can open these roads. And so, you know, kind of the first thing you do is you need to get out there and start doing that. But I mean, you know, you need to get out there first. I mean, here's the smoke hasn't cleared yet, and you get an indication of what that road and that area has been through. I mean, look at the volume of rock that's come down. Here's a loader opening the road just so you can get past it to check things out. Here's the guardrail here. It's been clobbered by rock. It's possibly been burnt. There's a hazard tree here. So this just kind of shows you the carnage that that area has experienced since those fires. Here's an area, you know, that obviously had a history of rockfall because here's a concrete barrier with a fence extension that looks quite old. I mean, that's been put in years ago to help increase the catchment ability of a pretty limited fallout area. And, you know, as we all drive by these, you see a couple of these that have some holes in them and whatnot. But just look at this failure event that occurred. You know, this is kind of a rock slide that just came down in such volume here that it shifted all this all the way across the road and blocked the road. And this is quite prevalent throughout the whole area through there. Here's an area that has some existing barriers with a fence extension. This is looks newer. I think this was put in after the 2014 fire event up there, and you can just see this thing's just completely overwhelmed. It's damaged. Here's all the rock that's made the road, and then I'll call your attention to this area here, all these indentation and pock marks you're seeing on the pavement. I mean, that is from rocks that have, you know, come bounded down the slope and impacted the road. So a lot of hazard, rockfall hazard that was prevalent before, it's really gotten active down there. I mean, we all know what a serious geohazard rockfall is, but I mean, here's a great reminder. You know, here's an ODOT truck that was up there assessing all these things, and I actually know the fella that was driving this truck. He left the site and was driving through an area that was thought to be kind of a lower hazard for rockfall and got nailed by two rocks as he drove out. And you can imagine if those rocks would have hit a launch feature a little higher on the slope and the elevation or trajectory of those rocks would have been higher, what the implications would be. So very hazardous situation out there right now. as Charlie mentioned, kind of what's an environmental hazard versus a geohazard. Something as a rockfall mitigation specialist, something we deal with a lot is trees. Trees on or along the crest of a rock slope, promotes rockfall activity. Sometimes we get a kind of loggerheads with the Forest Service and landscape architect types because, we don't like seeing trees within 10 to 15 feet of a crest of a slope because the roots grow down, they start growing into the fractures within rocks and they start prying them open. That's a phenomenon called root wedging. And then imagine a big tree with its roots really dug into a rock slope, and then that tree starts blowing in the wind. It acts like a giant pry bar, and that's called wind jacking. So even a good healthy tree is not the best thing in the world as far as rockfall is concerned. But now we have burnt trees, which are just a very difficult thing. It's new. Us in the industry are dealing with them since the Clackamas River Gorge fire and the fires out here. We're really having to get educated on trees and the hazards associated with falling trees. I mean, here's an example of some rockfall mitigation. This is an attenuator fence, and I'll show you some examples of those. That was installed after the 2014 fire. And look at the size of tree that fell on it. I mean, these things are great to protect the road against individual rock falls, but they're just not designed to handle a 4-foot diameter tree. And to give you some idea, the latest I heard from the Forest Service was there's an estimated 113,000 hazard trees along Oregon 224. And this was last week, and this has changed, but the last I heard that, approximately about 7,500 of them have been dealt with. This gives you an idea of what the crews out there are dealing with. So what do we do when we have some rockfall issues? What tools are in the mitigation toolbox to deal with them? Well, there's quite a number of things, but what's being most used out at along 224 is hand scaling, and that's the removal of the hazard itself, and that's where you have people on ropes that come down the slope under a controlled environment, and they use these pry bars and they remove all the loose rock off the slope just to get it off the slope. A next step up from that is heavy scaling, where you've got bigger columns or bigger blocks that the people just can't remove by hand. So they use hydraulic jacks, and back in the day, they used to use tractor jacks, long throw tractor jacks to do this. This is an example not at the Clackamas River, but along the Columbia River, where big columns been scaled off from there. Those jacks have been largely replaced by air pillows. Now quite common in the industry. These were developed by search and rescue and firefighting types to get debris off of trapped people and whatnot. And the scaling rockfall mitigation industries have adapted them quite well. You slide those down in the crack of a rock, you inflate it with an air compressor, and these things can lift 30, 50, 80 tons and of force to push these rocks off. So those are being utilized quite a bit out there to help with the rockfall situation. I'm going to just show you some examples of scaling out at the site, and just a series here. Hopefully your sound's good. You'll see a big rock get scaled off and you'll hear the thump and then the subsequent banging of the poor guardrail here. So here's additional scaling that's just being done out there. And here's an example, if you look up here on this, of a column that was one of those air pillows were used to scale off. So that's an example of the scaling, and you know, other things that's been done out there is drape mesh. I'm sure you're all familiar with seeing, you know, the chain link shiny mesh on slopes as you drive, you know, along the Santiam Highway and other places. It's quite common. It's come a long way since then. This is a high tensile strength mesh by GEO, and this material just conforms to the slope better, and it's treated with different stains that help it be a little more aesthetically pleasing and blend in with the background. I mean, you can see it through here, and that's standing there in the ditch looking at it, but a lot of times driving by, it's actually very hard to even notice some of that lately. Another thing that they're doing quite a bit out there is called an attenuator fence. I showed you an example where the tree hit. What that is a drape mesh, but instead of draping the entire slope with it, they come down on mid-slope benches, raise the mesh up on posts and wires, and the idea is any rocks that come down this slope will hit, its energy will be attenuated, and that rock will be trapped under the drape. And there's a rock right there, a good example. And then eventually this will work its way down and just drop down into the ditch. And it will, you know, these do a great job of keeping the rock fall from landing on the road, and instead put it on in the ditch where kind of regularly scheduled maintenance can come through there and clean the ditch. And they really offer great protection for the ODOT maintenance people that have to go out and clean these ditches. Here's an example of a attenuator fence that's installed. I think it's around milepost 35. I think this one was actually installed after the 2014 fires. So not only are they dealing with the issues out there now, but now they have to go through these areas and assess these fences to see if they've been somehow compromised by the recent fires. Kind of to come full circle here, if you remember the example that I talked about that was in the Federal Highways Manual of the top 10 slope in Oregon that I showed you along the Clackamas River, well, this is it. And you can see an attenuator fence has been constructed along the lower bench with it. So this is just an example of a very high hazard rock slope that with some bit of mitigation can really take one of the worst slopes in the state and make it safe for the traveling public here. Just thought I'd just go full circle on that. Now, before I wrap up here, we're going to leave the Clackamas River and head upslope a little bit. And this is in the area of near Oak Grove, near the Oak Grove powerhouse. And this is a PGE operated facility up there. And we've been recently up there helping them out with the same type of issues that ODOT's dealing with. And I just saw this and this blew my mind. When I first approached it, at first, you know, I'm like, is that a crucifix on the hill, or is that an old, you know, power pole on the hill? But you look at this one here and how burnt it is, you see the sag. This is only about 12 feet off the ground. And this is actually a power pole that was burnt in two, and just the line tension shifted that over. That's actually hanging in midair right there. I just found that kind of interesting. So here's looking at the slope near 3 links above the Oak Grove powerhouse. And this is a facility that we've helped PGE out with over the years. And this slope was a high rockfall hazard situation, producing a lot of rock back in 2018, 2019. And just on the right shows you what that looks like now after the burn. It's just devastation, and all this moss has been burned off and this rock heated up. So the rockfall activity is just increased by a huge amount. This is on top of that facility, looking down the famous penstocks here that go down to Oak Grove. And you can see on the left, this is a picture from 2018. Here's a picture following the fires that occurred up there. These penstocks are made famous by the Kevin Costner movie, The Postman, in 1997. I recommend, it's not a bad movie if that's your cup of tea, but Charlie and I have spent a lot of time walking around on these slopes. And then I'm going to turn it back over to Charlie, and he's going to talk about a very impressive landslide a little further up the river from this. So I'll turn it back to you, Charlie, and thank you all.
Thanks, Brent. Let's see if I can share my screen and get my presentation restarted. So Brent was just talking about some rockfall issues up above the Oak Grove power plant. Down in the bottom of this photograph, we're looking in this photograph from a helicopter. I think this photograph was taken in '97, if I recall right. In the bottom of the photograph, you can see the roof of the Oak Grove powerhouse. In the shadow, this line going up, this little white spot right here. I'm gonna go get my my fancy PowerPoint laser. Right in there is that structure that's up on the top where the water starts flowing down through the penstocks. I'll just draw your attention. There's kind of a steep sloped hill right here that kind of stands up around the ground. Around it, up above the Clackamas River. On the right side of the photograph, there's a little hint of part of the highway as it goes further upstream. On the left side of the photograph is this is the flow line that brings the water to the Oak Grove powerhouse. And we're looking at upstream as it goes up to an area that we call, it's a frog lake. It's a reservoir that's part of the conveyance system of bringing water into the powerhouse. On the far left are the upper slopes, steep slopes of Columbia River basalts that are exposed in this hillside. But basically, from the base of these slopes across the middle part of this photograph, and then just some irregular ground, and then it drops down a slope down to the Clackamas River and the highway right here. This is the beginning of a very large landslide complex that has been affecting the conditions of both the highway and the flow line system for decades. And let's see this. Next picture, this picture I think was taken in '90, and we're basically looking to basically downstream to the north and west. And in the distance is the Clackamas River, the middle Clackamas River Canyon that Brent was talking about. That's down in this narrow canyon. in the foreground, on the left side of the photograph, in the foreground, this is the Ripplebrook Ranger Station and their facilities, their resident facilities up there. Just a little bit beyond the Ripplebrook Ranger Station, you can see a little bit of the river hidden in the trees here. This is Timber Lake Job Corps. I think it's a job facility for folks up there. And this is this Frog Lake. This was back in '90 before some work that was done that made it a much smaller reservoir. But the things that you can basically see on in the hill slopes to the west of this area, the layers of rock in here, these are the Columbia River basalt layers in the lower half of the cliff slopes. In the upper part are the rhododendron formation. And then I think there may be some, well, that's maybe all rhododendron formation in the upper part. And that same materials are over here on the right side, where there's just Columbia River basalt cliffs and then the rhododendron formation up above it. And that's the same thing that you can see down in this drainage basin below. So basically from the base of these cliffs across this ground is this ancient landslide terrain that, I call it a paleo slide or an ancient slide. It's a geologic mapped formation. It's a pretty significant feature up here in this basin. I'm going to look at it a little bit with the LiDAR. So this is the LiDAR of the bare earth. So the trees have been processed out of the image, and we just basically see a bare ground image. You can see the river coming upstream. The Oak Grove Powerhouse is right here. On this slope is where that penstock is, bringing the water down. But this is a prominent little hill in this area. You can see follow the river going upstream all the way up to, here's the confluence with the Oak Grove Fork. Here's the Oak Grove Fork going off towards Timothy Lake towards the east. And then the Clackamas River keeps coming up to the south, going upstream here. But this whole area is pretty spectacular landslide conditions. The terrain is very irregular, hummocky ground. There's these long linear ridges that are giant blocks, slabs of Columbia River basalt that have moved at some geologic time and are tilted and rotated. I'm curious if early geologists thought that these were faults. Maybe that is a type of a fault, is like a normal fault. But they're very part of this landslide. There's a lot of different things that you can look at this, but let's take a couple closer looks at a couple parts. Okay, so this is the river, Clackamas River. Here's the highway. The road was reconstructed in, what year was it? I think it was the late 90s or mid 90s. Yeah. Mid 90s. And the rise in elevation from down when it's near the river up to this area is almost 300 feet. And this basically, the upper cliffs of the Columbia River basalt over here, the head of the ancient landslide is right in this area at the base of this slope. And then it's a very old, mature feature. The slide features are very subdued. There's not a lot of active scarps or movements. It's just like frozen in time kind of a landslide. But down at the toe, there's a lot more irregular, a lot more youthful kind of morphology, a lot sharper features. The old highway was constantly being affected by slumping ground. There were areas where there were 30 feet of asphalt where annual patching had accumulated over the years that was causing its own problems. But just this rise in the highway, they built the highway up on a large embankment. So as they drove into the landslide terrain, they would minimize cuts that had to be made to to maintain curve design needs and to raise it up above on top of the landslide. As soon as it started to cut into the landslide, every one of these cut slopes here is armored with rock buttress to add more strength into the ground to counteract the removal of the material from the cut. And it's behaved pretty well. I haven't seen a lot of maintenance over the years since then. But that's almost 300-foot elevation gain from the river up to this area up here. So just a little bit higher elevation again, looking back down. This is the area of the Frog Lake. The terrain is, there's a lot of, looks like folds and ripples and tears and shears in these things, but again, there's not a lot of youthful looking ground features. But down at the river, some of these features down here are creeping, active. They probably move every year, an inch, a half an inch or so. So the slide is moving at the toe, but it doesn't appear to be moving up here. And then same thing on the Oak Grove Fork. There's a lot of activity down at the toe, but the upper slopes on this bench do not appear to be moving. And we've gone up and looked for movements in the scarp of this ancient slide. There are some local features that look like their materials coming off the top. There's a little kind of a lobe of the slide, but there's no active scarp up in there. I'm going to just come back to this photograph to reorient yourself for the next slide. So again, the river's down here. Here's this Frog Lake, and then the steep slopes on the right. So this was a cross section that I drew back in the early 90s sometime. So there's a couple of instruments that are in the ground. I think there's actually 4 that are around the lake. This drawing doesn't have all of them, but basically it just shows you the rivers down here. There are exposures of the old Western Cascade material down at the toe. On the cliffs up above it, you have to, this overall slope is not as steep as a cliff, but definitely there's cliffs there, especially in the Grand Ronde and then the rhododendron formation up above. We don't have a lot of subsurface information across this landslide, but around the lake itself. So these instruments have been monitored since the early, when was it? Mid-90s. The movement that is observed in that is not like a classic landslide where everything's moving in one piece. There is movement going on. It averages about 0.02 of an inch, which not per year, which is not very much. But the other thing that's interesting about it, I think of it as like so the material is up to 300 feet thick. We have some deep instruments up there, and the material to me, I kind of think of it as a bunch of unconsolidated landslide debris, and it's not really like moving downhill. Now it is, because gravity's going and it's pulling downhill, but I kind of think of it as it shifts a little bit. Like one area, it kind of moves 1/100 of an inch, and then another area, it moves, and it doesn't relate to the seasonal groundwater. Some moves when the groundwater is high, but some of the ground is moved in the summertime. So it's not a classic landslide. It's more like a big pile of slide debris that is kind of settling over the years. And when did this start moving? We haven't tried to figure that out, but it's an ancient landslide. It's as old as the terrain is. How long has this river been cutting into the drainages and eroding? What are the overall erosion rates along the river? You can kind of go back and try to project when the conditions may have been in place that started the ground to move. It could have been back in the, 10,000 years or tens of thousands of years or 100,000 years ago. But anyway, that's the current condition right now. It's affected the lake, but PGE is maintaining it. They patch everything, and they reduced the size of the lake, so the lake is a much smaller impact on the ground, and they're able to maintain their system. Just a few more. Okay, so let's go a little bit further upstream. So here's the confluence with the Oak Grove Fork, Clackamas going to the south, Oak Grove going to the west. Here's the highway. Ripplebrook Ranger Station is right here. The highway comes in and makes the big curve, goes across the bridge, and then heads to the south up towards, if you go to Bagby Hot Springs, that's the road. You could also take the left and take this highway up towards Timothy. One thing I remember, I was driving down this road. I think I was camping in the late 90s, and I was driving down the road, and at some point I hit a drop in the road. So the pavement dropped like 4, 5, 6 inches, but the center line on the road had shifted to the west or to the right, like 2 feet. And then I was like, okay, I'm on a slide. And then I kept driving, and it was more than 1,000 feet later, bang, up the other side of the slide. The road had shifted back. Well, I had moved off the shifted ground, and I was looking at this LiDAR, and I was like, I think I can see where that movement is. But so the road's going down to here. Here's some slide terrain that is a little more youthful. This is in the same ancient landslide. There's some scarp features in here, but it's a lot older. It hasn't moved recently. And then there's a little subtle bulge right here. And that may be 2, 3 feet high or 5 feet or so. It's hard to tell. You can get the data and measure it from here, but this might be where movement was coming through that day that I saw it. And maybe this is the toe of a portion of this slide that moved back in the 90s. Anyway, it was just a thing that I was like, I always wondered where that slide was moving, but we haven't been working on it. The one thing on this image, this line, that's the limit of the LiDAR coverage. So everything else to the south doesn't have that, except for this isolated block further to the south. But before I go there, let's go upstream just a little bit. So here's the Ripplebrook Ranger Station is just off to the left of the image. And this is the Oak Grove Fork going up. And you can just see this, I can't remember the number of this road. It's 57, there's some forest road, but this landslide area right here, I think this has consistently caused problems for the forest. And then there's another one in this area that is even more commonly yeah, there it is. It's my laser's not showing it, but that area is routinely causing damage to that road. And then up above that in the terrain within the landslide, again, here's more of this ancient landslide terrain. Again, it's more it's a little more mature, hasn't moved recently compared to the materials that are down or the part of the slide that is closer to the river. So now I'm just going to go a little further upstream. I'm looking at the Colawash River. Okay, so the Clackamas River is further to the east. The Colawash River flowing, we're going upstream. Here's the highway. Here's the turnoff right here. If you can see, that image is a little bit washed out, but this is the turnoff to Bagby Hot Springs. If you turn right to go up to Bagby Hot Springs. But as you're going up this road, I don't know, I've never looked off to the left, but there's some creeks here. Here's one that's called Slide Creek. Okay, so if I just turn on the layer of the mapped landslides in the state, that this whole area is mapped as ancient landslides. So what the heck is what's going on? And this layer is the LiDAR first return. So this is the layer that's the top of the trees. So as the laser is shooting the ground, they're measuring the distance to the tops of the trees. This is the vegetation. You can see the areas where there's no trees, the clear cuts and things. But I just wanted to throw this in there because it's an interesting part of the LiDAR. But when you process it and remove the trees, you see what's on the ground up there. And I've never spent much time looking at this, but I have looked at some giant landslides up in the Cascades. And so here's the turnoff to Bagby Hot Springs right here. So just a few hundred feet downstream, this long, lengthy ribbon of a slide goes all the way up. I mean, this is almost 2 miles up in length going up to the top of this landslide. And the way that it's collecting up in this upper drainage, it looks like it spreads apart and spills over a cliff. There's another terrace, and then there's another slope going down to this broad, gentle slope, and it goes all the way around, turns a corner, and comes into the river. And it's not just a narrow slide. This whole area is just covered with ancient landslide terrain. And there's another one. Maybe these two are relatively active right now, but this whole area is landslide terrain. So now I'm curious, why did they go map this area? Why did they survey this area with someone looking in the forest at these landslides? And what are they contributing to the river and the environment and stuff? So I haven't ever hiked up there, but I do get to walk around on landslides. So maybe I'm not going to be looking at this one for professional duty, but as a recreational thing, it might be interesting to go up and take a look at this kind of slide feature. But that's the upper part of the drainage, and there's a lot of landslides up there. So take those into consideration when you're out hiking those trails in the valleys, and why the ground is hummocky and pavement is distressed. Thank you.
Excellent. Charlie and Brent, just superb, fascinating and content information there for us all. Are there any questions, Susie, that we need to get out and see if we can get our experts to answer them?
Well, I'll just add, in case Susie's away from her desk at the moment, we have a question from Gary Joaquin. Has an assessment been performed on 224 to estimate the scale of the funding required to address safety issues? If so, then what is that number? Can you describe the plan that ODOT has to mitigate this risk?
Yeah, I'm not aware of, obviously the road's been closed and they've been in there every day diligently working. I'm not helping ODOT at all with this. I'm more supporting PGE with their issues. But I was provided a lot of these pictures from colleagues that work for ODOT. I mean, I can only imagine. It's staggering. I mean, I do rockfall mitigation along roads all over the Pacific Northwest and the Western United States, and scaling and hazard tree removal and these drape meshes and these attenuator fences are not cheap. So I can only imagine the resources needed. Plus, like I mentioned, besides all that, it's this assessment of all this other infrastructure. It's just guardrail, it's culverts, it's existing bin walls and embankments. I mean, all these things have to be, if they're okay and survived and did not have any structural integrity issues, that's fine, but they still have to be assessed. So it's just it's a huge effort to do this work, as you can imagine.
I think that this was the only question. Pardon me, I was having technical difficulties and unable to get myself back on the screen. We did have one only one other question, which was asking about LiDAR mapping for Washington, and that is available through the USGS website.
Good. So Adam and Susie, any other questions in popping in?
I do not see anything new.
Okay.
That was
Well, I
very
just wanna-
thorough. Thank you.
I just want to thank again, Charlie and Brent for taking the time to do this. It was extremely informative. And I think for those that live in our community, hopefully they can get a greater appreciation of the actual devastation that's occurred here around us. So yeah, I'm taken aback. So with that, our next session will be on May 4th. It'll be our 4th geology class, and the presenter will be Katrin Chambers, a soil scientist with the Natural Resource Conservation Service. And Katrin will present an overview of the soils of our basin. So you can see now we're building up from the rock, right? I mean, we've been talking about the rock in quite detail, and now we're going to talk about the things that are happening above the rock and how the rock informs what's happening above it. So you can use the same Zoom meeting link that you did to log on tonight, and you're already registered for the event. And we'll send an email to you the day before. If you know other folks that are interested, please let them know, especially the younger folks. As you saw from our poll, you know, most of us are retired or those sort of thing. And I love it that we're wanting to learn more, but I really think that we should get more of the grandkids to involved in this to see what maybe future careers, or at least to gain a better sense of where it is in which they live. So we'll send you a thank you email with these links, as well as a link to the recording and more information about the continuing education units from Clackamas Community College. Again, our thanks to Charlie and Brent for an awesome talk tonight. And we also thank our gold sponsor, Clackamas Water Environment Services, and the bronze sponsors, the Clackamas River Water Providers, and the Geological Society of the Oregon Country, for helping us keep this conference free for all participants with their support. Every little bit helps, as I mentioned. So if you like what you see, please consider a small donation. Thanks again for joining us tonight. And please let us know what you thought of tonight's program. And we'll see you Tuesdays from now on May 4th. So thank you very much.